This is the online module, Drainage Water Management and Layout, New and Retrofit Design. This is one of 8 modules, as you see here. My name is Gary Sands. I'm a professor in Extension Engineering in the Department of Bioproducts and Biosystems Engineering at the University of Minnesota. I conduct extension and research programs aimed at the practice of artificial drainage. I also conduct most of the technical content of the trainings for the technical service provider trainings designed around the CAP 130. Today our learning objectives are the following. To look at how a drainage water management layout differs from a traditional drainage design, understand the concept of a drainage water management zone, look at the concept of zone elevation interval, understand the trade-off between drainage water management zone size and elevation interval, understand where to place zones and structures, and then look at the challenges of retrofitting this practice. Drainage water management differs from traditional drainage in that we use water control structures on the drainage system, and the system is designed and the layout is based on water management zones. The structures themselves are commercially available products. AgriDrain makes these products, ADS and Hancor makes these products as well. And we'll talk about the structure in the center there called the Watergate a little bit further on in the presentation. So it's important to understand the concept of a water management zone for this practice. And you see a field here pictured with a drainage system on the field with the light gray lines. So imagine a control structure were located at some strategic point on the main of the system, and then upstream or uphill from that structure, defined by the surface topography, there's an area of the field then that we expect to be able to manage the water table within that area. And so that area we refer to as a water management zone. So pictured here in the profile view, we have the same field, and here's the location of our structure at the corner of the field. And then this elevation interval, based on the field topography and the field contour lines, is a number that we will choose as the designer of this system. So based on the elevation interval that's chosen, it might be 6 inches, it might be 12 inches, it might be 1.5 feet or 2 feet. That determines the starting and stopping point for the zone. So here, if we were to locate a structure at this point in the corner of the field and set our desired depth with the water control structure as indicated by the dark line in the middle of the structure, then we would expect the water table to look like this throughout that zone. What do you think of this illustration? Is there something wrong with this picture? Indeed there is. In fact, we know that water wants to seek a horizontal or level condition with respect to the land surface. And so what that means is that as we go back up into the zone, away from the structure, that is upstream or uphill from the structure, the water table is actually farther and farther off of our target depth, indicated by this red wedge here and the illustration in the upper right hand portion of the slide. And at this point then, we would locate another structure in the field for the second zone, and we would be back at the desired water table depth, and then we would move up into that next zone on the field. So that's, in general, the concept of the zone and the elevation interval. Those two parameters kind of go hand in hand for these systems. Here's an example with numbers. We have an elevation interval here of 1.5 feet. We have a starting elevation of 6 feet. We have an elevation of 7.5 feet on the top end of the zone. And so what that means is that, again, on the high end of the zone, for this scenario, we're going to be 1.5 feet off of our desired depth. If we have a target water table depth of 2 feet, and that's our water table depth in the structure itself, on the high end of the zone, we're going to be at 2 plus 1.5, or 3.5 feet of depth. So it would be 1.5 feet off of our target depth. So as you might imagine, there's a trade-off here between a small elevation interval and a large zone. We would like, as a designer and a planner, to choose a very small elevation interval because we have a greater degree of control over the water table. We have a more uniform water table. The agronomic impacts of the practice may in fact be greater with a higher degree of control. But a smaller elevation interval is going to lead to more zones and a higher cost. On the other hand, we want to strive toward large zones for this practice. Every zone is going to have a control structure, and the larger the zone, the fewer of them there will be, and the fewer structures we have in the field, bringing the cost down. There's also a management consideration here, in that for the most part, every structure is a management point now for the field. And the more structures we have, the greater the management effort is going to be required on an annual basis. Topography either makes or breaks us for drainage water management. And if you'll forgive the gimmicky slides here, they really help to drive a point home though. If our field is flat, it's very favorable for drainage water management. The flatter the better. If our field is flat as a pancake, then our drainage design really doesn't matter. Again, flat as a pancake, we're looking at locating maybe one structure on the outlet of the system and then being able to control all of the acres in the field with that one structure. In the ideal case, where the field is perfectly flat. But that's not often the case for much of the drained part of the Midwest. Oftentimes, we have some slope in the field, as we see depicted here. And when our traditional drainage system or a new system is designed so that the laterals go up and down the field and the mains are put on the flat part of the landscape, we don't have much of an opportunity to manage the water table. You see here one structure located at the outlet, and we pick up a portion of the field in terms of management, and there really isn't a good place to locate a second structure. However, if we have the opportunity to design this field with drainage water management in mind, we're able to locate the laterals more aligned with the contours and then put the mains up and down the steepest parts of the field. Now this makes sense for traditional drainage anyway, because laterals are going to be more effective when they're on the contour and they're intercepting water as it moves down slope. And when mains can be located on the steepest grades in the field, the size of main lines can be reduced. But for drainage water management, it's critical to lay out a system in this fashion. And again, one of the things that we stress in our drainage workshops every year is that we want to try to put laterals aligned with the contours as shown on the left, not on the right. And this again is another illustration of what it might look like to sort of stair step a water table up a slope. This is obviously exaggerated, but it helps to kind of drive the point home here. So topography matters and design matters as well. When topography gets really flat, design is less of an issue. As topography as we start to see more and more slope in a field, design becomes more and more critical, and more planning is necessary. It's very important, and one of the points that we stress very heavily in our drainage design workshops is to design with drainage water management in mind. Because like the example we saw earlier, when we put laterals in that go up and down the slopes, these fields are never going to be able to have this practice implemented. These are the designs for the field that we just saw in the aerial shot. On the left was the design, the traditional design that was going to be implemented, with laterals more or less going up and down the slopes of the field. And the design on the right is the drainage water management design. You'll notice that these laterals, indicated with the blue and green colors, are located on the contours. The contour lines are not shown here. So there's no opportunity to manage this field on the left if this design had been implemented. And the field on the right has drainage water management capability. And again, I like to stress that even if the practice of drainage water management is not going to be implemented right away, if the design is right, the practice can be dropped in and retrofitted anytime in the future. But if the design doesn't accommodate the practice, then it will be an opportunity missed forever. We saw an image of this structure on a previous slide, and it's worth making a few comments here because it does affect the design of these systems. This structure, called a Watergate structure, is an inline structure. It does not come up to the ground surface like the traditional structure as shown here. And so these operate and work on kind of a master-slave concept, where the first structure in the field, as shown at on the far right of the illustration here, the first structure is going to be a traditional structure, and then the structures upstream of that will be these Watergate structures. And they operate on a principle of a 1 foot head difference. So wherever I set the desired water table depth in this bottom structure, and I'm not sure if you can see my pointer here, but where I set the water table depth in my bottom structure, the next Watergate structure upstream is going to see that water level, and it's going to add a foot of head to it. And then that translates up to the next Watergate structure upstream, and it sees that water level, and again adds another foot of head to it. So it's important to keep in mind that for this particular structure, the elevation interval for the zone cannot be greater than 1 foot. We often get questions about the grade of the main or the submain where the structures are located. What if it's a steeper grade? What if it's a flatter grade? Does this matter? And when you think about it, you look at this particular illustration here, none of these pipe configurations really matter when it comes to what's going on between the desired water table depth and the ground surface. It's all about where the water table is with respect to the ground surface and the topography. It's not about where the pipe is located or the grade that the pipe is on. Now, for this last option here, this does matter, obviously, because now we have a desired water table depth that is below or deeper than the tile on the upstream portion of this particular pipe. So in this case, it would matter. If my zone were considered to be extending all the way to the right in this figure, part of it is not going to be functional at certain water table depths. Let's look at a few planning and design rules of thumb then. For starters, flat field topographies. Flatter fields really favor this practice. Perhaps the outside range would be 0 to 1% grades, but 0 to 0.5 grade would be even better. The field I showed you earlier with the aerial shot, the quarter section, with the traditional and drainage water management design, that field had about a 1% grade in it. And that's pretty extreme for this practice. it's going to drive the cost up. We've got a broader set of goals here than a traditional drainage system. We've got agronomic goals that are even a little different than traditional drainage. We've also got some water quality goals. So these should be on the table when designers and installers talk with their clients. We also have the use of new equipment for these systems. We did not have drainage water management structures, control structures in a traditional system, so that's another thing to consider. And we also have the management component now that will need to be discussed with the client. And this wasn't the case in a traditional drainage system, sort of put it in and forget about it for the classical drainage system. But with these systems, management is very important and needs to be discussed. So those are a few things to keep in mind with regard to the planning and design of these systems. In terms of the design steps for drainage water management, there are a few steps here that are going to be unique to these systems. We need to look at that elevation interval for the zones themselves. We need to figure out where the zones are going to be and determine the location of the structures that will serve those zones. Remember, every drainage water management zone has its own structure. Okay? So after those three steps, though, the rest of the steps required for designing the drainage system fall in the category of traditional design. Everything else here you have to do in the design of a traditional drainage system, with the exception of the last step here, the discussion of water management plan with the client. But everything else is traditional drainage stuff after we get finished with the first three steps. One way to look at that graphically here is as I'm showing here. What we're doing is adding on a bit of extra work when it comes to the layout of the system. And this field zoning, as I would call it here, is the extra step that we have to do. And everything else is pretty much traditional drainage. I'd like to take you through a couple of design examples now to drive these points home. Here we have a topography, a field topo, that goes from about 42 feet down in the lower right-hand corner to about 46 feet in the upper left-hand corner. And what I'm showing here is a traditional drainage system with laterals going up and down the contours and the main line going across the bottom of the field. And if you were to put a structure on this field on the 42-foot contour line, as I've done here, and delineate a zone with an elevation interval of, I think I'm using 1.5 feet here, so I go from 42 feet to 43.5 feet. You get the blue zone as illustrated, and then where would you put another structure? There really is no place to put a second structure, so you're very limited. Again, trying to drive this point home, you're very limited here in terms of what you can do with this field if it's set up in a traditional drainage layout. But if we were to take this and split it into a couple of zones, and I'm going to split it here on the 44-foot contour line. So I'm going to divide it into two zones, each with an elevation interval of 2 feet. And those are shown here in green and blue, and call these two different drainage water management zones. So every zone, as I mentioned, is served by its own control structure, and we can think about these structures as being the outlet for that zone. So all of the pipe and the layout in a zone has to be plumbed through the structure that serves that zone. So typically for these systems, we don't have drainage laterals that span from one zone into the other. And so I've got a couple of examples here for this field. So here we might see one option for locating control structures. Now the control structures need to be at the low elevation for that zone, but they could be anywhere on the lowest elevation. We'd like to keep them on the edge of the field, obviously. We don't want to create another obstacle for the farmer in the field. So here's an option with both structures located on the east side of the field. And then the drainage layout within each zone could look something like I'm showing here. Now, I haven't drawn in all the lines, and certainly they're not drawn to scale in terms of drain spacing and so forth, but I think you get the idea that each zone now has its own sub-layout, if you will, where all of those, where that portion of the system will drain into the structure for that zone. And we could do this differently. Here I'm showing now structures in different locations than the first option, and the layout might look a little different in this case. Or we could decide to break this field into more than 2 zones. We could reduce the elevation interval, and by doing so, we're going to reduce the size of the zone as well. We're going to create more zones. Here's an option with 4 zones for this field and 4 structures for those zones. Now, all of those structures need not be connected together with a submain, depending on what the regulations are for the outlet. Each structure could have its own outlet pipe, or they could be connected together however is convenient and required for that particular field. And another option here where we break the field into 3 1.5 foot zones. 3 zones here. So part of, well, not part of, but a significant aspect to planning these systems is figuring out what the field is giving us. Remember, we're trying to balance the size of the zone with the size of the elevation interval. Trying to reduce the elevation interval where possible and try to increase the size of the zone where possible. And here's one scenario for locating structures for this particular plan. Now, which one are you going to go with? There is no right and wrong here. Every field is going to be its own special case, and every client is going to be different. So, is it going to be 2 zones, 3 zones, 4 zones for your field, or is it going to be 1 zone? There are many fields where you've got a portion of the topography in the field sets up very nicely for 1 zone and not much available after that. So it's up to the planner and designer and the client, working with the client, to figure out what is the best option for that particular field. Here are a few other examples borrowed from clients. This one and the next couple from Dr. Bud Belcher. And this is a field broken up into 3 zones, I believe, for sub-irrigation. But the concept of the zones is really identical to that of drainage water management. You see a portion of this field in the upper right-hand corner where no management is being done. The topography is such that it doesn't lend itself to this particular practice. Here's another field broken up into 3 zones as well. So it helps to just see a number of different scenarios. We're going to work through some scenarios together as well here before we get to the end of the module, and I give you a little practice at looking at these zones. You're perhaps going to be seeing plans, drainage water management plans, that are drawn up using all kinds of different tools. This is, you'll see shaded and colorized topography. This one happens to be contour lines in yellow in a layer over top of the aerial image. These are 1 foot contours here. No, excuse me, these are 2 foot contours. So you're going to see these plans come in all different shapes and sizes and tools. This happens to be both a contour line and a shaded contour interval based on some LiDAR data here. I think the contour lines are at 1 foot with the shading going 1.5 feet. For this practice to be successful in the Midwest, it's going to require retrofitting in many situations in fields where that have already been drained, where the drains are working effectively. They're not going to be redrained. We're going to have to retrofit the practice where possible. So it's worth spending a couple of minutes talking about what retrofits would look like. Here's that system that we looked at a little while ago, and with the traditional laterals going up and down the slopes. And after you put the one structure there and pick up a few acres, you really don't have an opportunity to place another structure there and pick up any additional significant area in the field. What would we have to do to this system to be able to pick up a greater percentage of the field with the practice? It's going to mean coming in with some additional mainline and doing some additional plumbing for the field. So here's just a quick and dirty illustration that I did for this field and what a retrofit might look like. So here we see two structures located on the right side of the field here, the eastern side of the field. I've got two zones, each with a 2-foot elevation interval. And the black lines here, the heavy black lines, indicate the new submain that's going to be required to get this job done. So the one that goes across the middle of the field, this is going to require new connections to all of those laterals. The laterals are going to have to be broken and reconnected to this new submain. And then the submain that runs down the eastern side of the field so that that structure can be outletted properly. This is not going to be cheap. It's going to take a lot of effort, but in certain scenarios where you can pick up enough acres on a structure, it's probably going to be feasible. And again, for the practice to really be effective, we're going to have to look for all the retrofit situations possible. So here are a few summary points with regard to the concept and planning of drainage water management. We've got a few extra design considerations, that is, compared to traditional drainage systems. We're going to be looking at crop yield in a different way than a traditional system. We've got water quality issues and goals on the table. We've got flow reduction, hydrology considerations, and we've got the management of these systems to consider. So we've got more things to think about when it comes to a drainage water management design. The field zoning is the major difference and the point of departure from conventional drainage design. We always tell our practitioners that just because we're doing drainage water management doesn't mean that we get to forget about making good choices for drain spacing. We still need to do that, drain spacing and drain depth. And remember that there are going to be important management considerations for these fields. Consider the trade-offs, crop yield versus the environment. Again, these are things that come into play for drainage water management systems that don't necessarily for conventional drainage systems. And then last but not least, design with drainage water management in mind so that the practice can be retrofit later. And again, I'll reiterate a point I made before. When design is done without this practice in mind, especially for fields that have some degree of slope to them, it's going to be an opportunity lost for a lifetime, really, because we're not going to get to go back and retrofit the practice if the design is not well suited. Now we're at the point where you get to try your hand with some planning and design. There are 3 handouts that come along with this exercise that if you have not already printed out, I'd like you to hit pause and print out before we go further. These are the 3 fields that are shown on this slide right here, so you should have 3 pages of handouts. The first field we're calling Retrofit Design A, and go ahead and find your handout that matches this field, and then press pause so we can go through the hands-on exercise together. Have you paused? Okay, let's begin. Here's the exercise. What I'd like to have you do is, for this field and existing drainage system, I'm going to give you 2 drainage control structures, 2 water control structures that you have at your disposal, and you get to put them anywhere you want. And I would like you to figure out or decide where to place these structures on this main, where to place the structures, and then I would like you to delineate the zone that is affected then by that structure or those structures. So you could use an elevation interval of 1.5 feet if you'd like, or you could use 2 feet if you'd like. So you decide where you'd like to place your structures and then delineate the zones that are going to be influenced then by those structures given the elevation interval of your choice. Go ahead and take a few minutes to do that, and then I'm going to sketch out a couple of possibilities here to continue. So by now you've got something on your paper, and I'm just going to pull up my iPad here and do a little sketching live on this field. So our field elevation at the outlet is 5.5 feet. Let's just say for starters that I want to put a structure right at the outlet located at the 5.5 foot elevation. And so then I'm going to draw that in. I've got a structure right here at 5.5 feet. And let me then sketch in a zone for a 2 foot elevation interval. That would go then from the 5.5 foot contour to the 7.5 foot contour, and it would look something like this. And I'll just kind of shade that in for us here. So that's my first structure, and not bad actually. This is a 120-acre field, and I've picked up maybe just shy of 50% of that field just by placing one structure at the outlet. Now, where would a second structure go if I were going to try to use it? Well, it's probably going to go somewhere along the main. So as I look now to the right along the main from the first structure, where would I place it? Maybe I would place it here where the 6 foot contour line crosses the main. Let me switch colors, and that would be something in like right about here. Maybe I would place my second structure there. But what would I get with that? So with a 2 foot elevation interval going from 6 to 8 feet, okay, what does that zone look like? It looks like the following. It looks like this. So really all I've gained with that second structure is this area right in here between the 7.5 and 8 foot contour line. Granted, for this part of the zone in here, I do achieve a greater degree of water level control than if I had just left that structure off. But in terms of impacting new acres, new area, the second structure really has not gained me very much. So that's a take-home lesson right there. With this particular retrofit, where we've got the laterals that are going up and down the slopes, it's not particularly well suited. Even though we did pick up about 40% of the acres or so with that first structure, it's not particularly well suited for drainage water management. So let's go ahead to the next handout then, and then I would like to have you hit pause again and consider this second field for your next hands-on exercise. Here we have the same field, but now the drainage system is oriented in the opposite direction. So the laterals are going east and west, and the main is going up and down the west side of the field there. So go ahead, if you haven't already, press pause and take a few minutes to do the same exercise. I'm going to give you 2 structures to use, and I'd like you to place them along the main there, and then sketch out the zone of influence for the results from those 2 structures. Okay, so hopefully you've got something on your paper there now. Let's go ahead and talk about it and look at a couple of possibilities for this field. So let's start with a structure, again, like we did before, located at the outlet. Let's say the 5.5 foot contour line down here at the outlet. And let's again go with a 2-foot elevation interval. So I'm going to shade that in. And that would go from 5.5 feet to 7.5 feet. And that would be this zone right here. All right. And I'm just going to shade that in. There's my first zone. So I would then place my second structure at 7.5 feet, like so. And then that zone would go from 7.5 to 9.5 feet. So that would go up here, all the way over there to 9.5, down the 9.5 line. But how far can I go? What can I shade in here? Actually, I can only go this far. Like this. What that means is that this area over here falls outside of both of those zones. Now, why was I not able to include that area in my purple zone there, in my zone number 2? Simply because the pipes over here, where are they connected? They do not flow into my second structure. They are connected into the blue zone. So they fall outside of my second zone and are not picked up by either zone. Given that it's a 2-foot elevation interval. Is that, I hope that's clear. Now, as we look at this, here we were able to pretty effectively use 2 structures and pick up what percent of this field would you say? Close to 80% maybe of the area of this field. Why did it turn out so much better for Retrofit Design B compared to Retrofit Design A? Why do you think that is? The answer is because the laterals here are much more aligned with the field contours. Even though it is an existing system, even though it's a retrofit, it just so happens the laterals are aligned pretty nicely with the contours. And as a result of that, the field sets up much better for drainage water management. Now, there are other ways you could look at this. You could look at a smaller elevation interval, perhaps, and maybe put 3 structures out there, but you're probably not going to pick up any more area of the field by doing so. So the lesson here is that just due to the orientation of the laterals, it ends up being a much better candidate for our retrofit than our retrofit design A. Okay. So let's move on then to our next example. And this is our 3rd shot at this field. And guess what? There's no drainage system here now. Now's the time for you to imagine a drainage layout that would try to pick up all of the area of the field with drainage water management. So I'd like you to think about how you would modify either one of those previous layouts, or come up with some new approach altogether, and use as many structures as you need to try to manage, close to 100% of this field. So hit the pause button, and I'd like you to spend a few minutes with this field. This is going to take you a little longer than the first 2, because you have to envision a new plan, a new layout here. So hit the pause button and take 5 or 10 minutes if you need to, and sketch this out on your field. And then I'll draw in a few possibilities here on my end, just as food for thought. So by now, I'm sure you've got a few ideas down on paper, and let me just do a little coloring here on my own. I'm using an iPad, by the way, connected with my notebook computer to give me a drawing or an annotation overlay over top of my slide, just in case you're wondering how I'm doing this. So I'm going to turn on my coloring tools, and when I look at a new field like this, it's important for me, and the way I like to start is to select the zones and sort of color those so that I can see what the zones look like. And then I go about placing structures and figuring out the drainage network inside of those zones. So let me start then with looking at what do I want to do here? A 2-foot contour. No, I'm going to do a 1.5-foot contour. Since I'm designing the system, I'd like to cut back on that elevation interval, get a little higher degree of water table control. So I'm going to start at the 5.5 elevation and go to 7 feet for my first zone. And I'm going to sketch that out here in blue. I'll go from 5.5 feet to 7. So there's zone 1. Went outside the lines a little bit there. The next zone is going to go from 7 to 8.5. 7 to 8.5. Like so. And the third zone will go from 8.5 up to the corner of the field. That'll be my third zone right there. Now I've got to decide how I want to, where I'd like to place structures, and where the main will go, and then where the laterals will go. For the first scenario, I like to start simple and just put in laterals along the, put in a main along the west side of the field over here. And I would like to locate my structures over there. So here is my first structure, for my blue zone, my second structure for my green zone, and let's assume that I'll get my third structure up here. Where then is the drainage network going to go, or the layout going to go, to make that work? I could stay with these east-west orientation. Oops, it looks like I've lost my connection here. Just give me a moment. So I'll continue drawing those laterals in. Oops, I got to back up a little bit. I lost some of my annotation. So I'm going with a main down the west side of the field here, and structures located at the outlet at 7 feet and at 8.5 feet, like so. And then my laterals, I could stay with that east-west orientation like I had before. Now notice these laterals stay within this blue zone, obviously not to scale here. And then the last lateral I just drew has to come in downstream of that second structure. And then for my next zone up, my laterals perhaps could do something like this. And I'm going to have to get laterals down here. And I could do this a number of ways, but I could do something like this. And then for my third zone, it could do perhaps something like this. Now, of course, the designer and the installer, they have to be concerned about being able to get adequate grade and that sort of thing. So I'm just putting these in kind of quick and dirty, just so you can get an idea of what the layout perhaps might need to look like to make this work. You probably had something else on your paper than what I just drew here. So let me back up and do something a little different. Let me clear that off. And what if I wanted to perhaps go up through the middle of the field? So I could go this direction with a main. And again, I had zones as before. My first zone goes to 7. My second zone goes to 8.5. And my third zone is up at the top of the field. Now where are the structures going to go? My first structure could go at the outlet, or it could go where the main takes a right turn. Let's put it down here for my first structure. My second structure then is going to go up here, and my third structure is going to go up here. And now I get to do something different perhaps with my layout. For my blue zone, these could go this direction. And keep the orientation straight. And then for the next zone up, I could stay with this orientation on the left side and then do some kind of an angle on the right side. And I think you're getting the idea now. Could even do something like this. All right. A little bit sloppy, outside the lines a little bit, but I think you get the idea. Let's look at one more scenario here. What if we wanted to place structures along the east side of the field so that we ran a submain over here and then up to here. So my first structure, as before, is down here at 5.5. My second one is at 7 over here. And my third is at the 8.5-foot line. That keeps my structures out of the middle of the field. Might not be a bad option. These structures over here on the east side, perhaps these could drain straight to the outlet. And if that's the case, I don't even need this main, but my main could, I could have a main like this, and laterals in my bottom zone that do something like this, and then laterals in the next zone that do this. And I think you get the idea there. Some of you may have been thinking about the fact that we've been putting that first structure down here at 5.5 feet. Yet, there's only a portion of the field, just the edge of the field, that is at that elevation. Wouldn't it be nice if we could place that first structure at 6 feet? And in fact, that is something we could consider. And I've got a little sketch on the next slide that that considers that option. So here's a scenario where we place our structure at the corner of the field, but we manage it as if we manage it based on the 6-foot contour line. Okay. So if we have a 2-foot zone, we go from 6 to 8 feet, perhaps. Here, as I'm showing here, it's a 1.5-foot zone, from 6 to 7.5 feet. But what happens on the portion of the field that is below 6 feet in elevation? So I've shown this in a profile sketch here, and we see the red wedge as before. As we go up into our zone, we get farther and farther off of our target depth. In this case, my example here is a 2.5 target depth, water table depth. and that starts at 6 feet at the beginning of the zone, and at the top edge of the zone at 7.5 feet, you see that I'm 1.5 feet deeper than my target depth. Okay, we talked about this before. So what's happening from between the structure, which is at 5.5 feet, and the 6-foot contour line? Well, as I've tried to indicate in my field illustration up there, what's happening now is we're also going to be off from our target depth, but in the opposite direction. So as we go from the structure up to 6 feet, our water table depth is actually shallower than our target. Okay, shallower than our target. So we're managing around 6 feet, but the field is only at 5.5 feet down there. So as I get closer and closer to the structure, I'm shallower and shallower, or further and further off of my target depth. Too shallow instead of too deep. So this is something to keep in mind. And I've seen a number of situations where, we place a structure in one place to manage a zone that's not sort of contiguous to the location of that structure. And this could be an issue, if we're trying to be very aggressive and manage very shallow water tables. It could lead to ponding, for instance, on a portion of the field. And in this particular example, we're on the edge of the field. Is this a part of the field that's going to see a lot of traffic? Or are there going to be issues during various times of the year when we're trying to manage very shallow water tables? So this would be something to consider in terms of the management. But is it possible to do? Yes, it is possible to do with due consideration of the potential consequences. What I'd like you to do for our last exercise is to consider that first field again. This is our first retrofit design. I'm calling it A1 now. And I'd like you to consider what might be needed if we were going to try to get a second structure in here and pick up a greater percentage of this field. So I'd like you to hit the pause key, and if you don't have 2 copies of this field, you can scribble over top of the first one you did, or perhaps you want to print out another one and go from scratch on that. But go ahead and hit pause, and I'd like you now to use 2 structures, 3 if you'd like to, spend the time to do it, but use 2 structures and consider where you would have to put new pipe to add a second zone onto this field. Go ahead and take a few minutes and see what you can come up with, and then I'll look at the possibility here. Okay, let's take a look at this. So I'm going to place my first structure down here as before at the outlet. And so my first zone is going to be, as before, I'm going to go up to, I'm going to make this a 2-foot elevation interval. So I'm going to go from 5.5 feet to 7.5 feet. So there's zone 1, and that was what we did in retrofit A, and we said that there really isn't an option for putting in a second structure. But now we get to put in some new pipe if needed. So what would we do here? So let's say our second structure is going to go in over here at 7.5 feet. At the 7.5-foot contour line over here. But now in order to use that, I've got to get some new pipe installed to make this work. I've got to connect this structure either to the outlet or to the existing main, as I've indicated down here in the lower corner. And then I've got to put in an additional main coming across here. And that will allow me to go from 7.5 feet up to 9.5 feet. And I'm going to have to establish obviously new connections on each one of these laterals, as you see here. So with somewhere around 2,800 feet of new submain, plus the work required to cut those laterals and reconnect them to the new main, I'm going to now pick up probably 90% of this field. So how did yours turn out? I'm wondering what your version might look like. Here's something I'm not going to ask you to spend any time drawing, but let's just think about it for a second. What would our zones look like for a field like this? Don't be fooled by the contour lines. Even though I've got 3 contour lines running through this field, if you look at the spot elevations, we really only have about 6, slightly more than 6 inches of elevation change across this field. We go from 100 feet at the outlet up to a high point of 100.6 down in the corner there, in the bottom right corner. So this is an example of that flat as a pancake field, where you could place one structure at the outlet and basically call the whole zone, call the whole field your water management zone. And this is as good as it gets when it comes to drainage water management. And at this point, it really doesn't matter what kind of drainage layout is on this field, where the laterals go, where the submain goes, because one structure can pretty much pick up the entire field. Now, if this happened to be a pumped field with a pumped outlet, that pumping point, that lift station, could in fact be the control point for this field as well. So we've gone through conceptually what it takes to plan and design a drainage water management system. We've looked at the concept of the water control structure. We've looked at the concept of the zone, the concept of the elevation interval, and we've looked at the interplay between the size of the zone and the size of the elevation interval. And we then looked at several hands-on examples, sort of exploring different options for a number of different contours. Obviously, we looked at a very narrow range of possibilities with only a few fields, only a few contours. And if you work with this practice and start to look at and perhaps approve plans that come into your office, you're going to see, I'm sure, a wide range, much wider than we have time to go into today. But hopefully, at least, you're out of the blocks and you've got a good start on knowing what it takes to size up a field and understand what the field is giving us in terms of zone management zones and so forth. I invite you to contact me if you have questions. My email address is here. I'd be happy to clarify anything that with regard to this particular online module, or answer any questions that may come up as a result of any of the modules or any of the work that you do. Thanks for your time, and hope to see you at one of the on-site trainings.